In this lesson, we're going to discuss the concept of a matrix inverse. But before we get to that, we have some terminology and some skills we need to put together so we can find those inverses. First, we need to review the idea of a square matrix. Square matrices have the same number of rows as columns, 2 by 2s, 3 by 3s, 4 by 4s. We also have to talk about this identity, this idea of a multiplicative identity. An identity would also be a square matrix with ones down the main diagonal, zeros everywhere else. What we're looking at today is a multiplicative inverse. So here's how it's defined. If A and B are square matrices, and I multiply A and B, and it doesn't matter which order, and I get one of these multiplicative identities, then A and B are multiplicative inverses of each other. Now, some terminology and some notation. The inverse of matrix A is denoted with this A and a little -1. There's no arithmetic there. That just stands for inverse of matrix A. So, I've got two matrices here, A and B, and I wanted to determine if they are inverses of one another. So the question might read, determine if matrix A and B are inverses. What they're asking you to do is to multiply these two matrices and see what you get. So when I multiply A and B, I get a 1, then I get a 0, I get a 0, and I get a 1. Now, if I turn that around, if I instead take matrix B, so rows here, columns over here, and I multiply this out, I get 1, 0, 0, and 1. So it didn't matter which way I multiplied them, I got 1, 0, 0, 1, which is an identity. Let's try another one of these. So I'm going to multiply C times D to decide if these are inverses. So I multiply 2 and 2, 4 and -1. I already know that's not going to be an inverse. I'm supposed to have ones down the main diagonal. I could keep going, but it's not getting any better. Definitely aren't inverses. I did not get that multiplicative identity. And this works for 2 by 2s and 3 by 3s. So the first skill that we need before we get to actually finding these matrix inverses is an idea of a determinant. Now, a determinant only works with square matrices. Everything we've done today has to do with square matrices. And here's your notation. It's a DET, which is short for determinant, and our capital A, which stands for our matrix, or if they give you the matrix and put DET in front of it. We'll start with the easy one, the 2 by 2. So if I have a 2 by 2 matrix, and they want me to find the determinant of that 2 by 2 matrix, I take the main diagonal and I multiply them. I take the backwards diagonal, multiply them, and I subtract those two numbers. And I will get a single number. I don't get another matrix, it's just a number answer. So my example up here, 3 times 5, and -1 times 2. So I have 15 and -2, and I am supposed to subtract those two things. So 15 minus a -2, the determinant is 17. The arithmetic is not strenuous, and the minus sign sometimes catches people off guard. Now, for a 3 by 3 matrix, it's a little more involved. So here's how it's defined. They gave you this 3 by 3 matrix, and they've got all these products in here, A1, B2, C3. They've got all these products, and you'll notice that some of them are being added, and some of them are being subtracted. I'm going to give you a different method for doing this. This is called the diagonal method. So I took the matrix, and I rewrote the first column and the second column another time. And I'm going to look at 4 diagonals. So right here, A1, B2, C3. That's where I came up with that product. I multiply those three numbers. Then the next forward diagonal is B1, C2, A3. That diagonal right there. And the last forward diagonal is C1, A2, and B3 right there. Now I wouldn't be able to do this if I hadn't first rewritten those two columns. Now when I work backwards, I'll use a different color for the backwards one. Now when I look at the backwards diagonals, B1, A2, C3, A1, C2, B3, and C1, B2, A3, that's where I'm getting these three products. But because we're going backwards with them, I am subtracting those three products. So this is how you do a 3 by 3. There's another method called expansion by minors. If you're interested in a different way, a little more complicated in my opinion, you can certainly research that, but this is called the diagonal method. And I'm going to use an actual example to do this. So here's my matrix. And I'm going to take the first two columns and rewrite them. So I rewrote the 1, 0, 3, and I'm going to rewrite the 0, 4, and 5. So now that I have those rewritten, I need to look at forward angles. So I'm going to multiply these three things right here, 1, 4, and 2. Then I'm going to multiply the next one, 0, negative 1, and 3. And the last one, negative 2, 0, and 5. And I'm going to add those three. They are the forward angles. I'm going to add them. Now I'm looking at backwards angles, 0, 0, and 2, 1, negative 1, and 5, negative 2, 4, and 3, and I need to subtract these angles, or these diagonals. The plussing and the minusing is usually where people get hung up. So I end up with an 8, 0, 0, 0. This is a plus 5. Minus, minus, that's a plus 24. Those add up to 37. This has a determinant of 37. Our determinant is always a single number that comes out of that matrix. So the last thing that we have to do is to get to this inverse. We now have the skills where we can actually do them. And we're going to stick with 2 by 2 matrices, square matrices for now. So here's my sample, A, B, C, and D. And notice the first thing they ask for is the determinant. Now if the determinant happens to be 0, you are done. There is no inverse. You cannot do an inverse if the determinant is 0. So that's why we learned about the determinants first. If the determinant is anything but 0, then we can actually find this inverse. Here's my notation, A inverse, that little negative 1. It says I should do 1 over the determinant. That's why I did the determinant first. And then this got rearranged. Notice that the A and the D switched places. The B and the C didn't move, but they changed sign. So I'll say that again. 1 over the determinant. A and D, this main diagonal, switch places. The B and the C stay put, but they do change signs. Negatives become positives, positives become negatives. And all this is the same writing, but with what the determinant is, which we learned in the earlier part of this video. So let's do an example of this. We'll start with the determinant. I'm going to take the main diagonal minus the backwards diagonal. So I get negative 9 plus 6, I get negative 3. I know it has an inverse. So I'm going to put 1 over negative 3, and now I need to rearrange. These two are going to change places. So this 3 goes up here, this negative 3 goes down here. The 6 and the negative 1 aren't going to move, but the 6 is going to become negative, the negative 1 is going to become positive. there it is as an answer. You can certainly leave them this way, but if you go to back of a textbook, or if you look these on or use a calculator, they're gonna multiply the negative 1/3 in. I don't mind if you leave them separate. It helps us with our next activity. But if you would multiply these in, you're gonna get something that looks like this. Either one of those answers is acceptable. We have to remember to do the determinant first. Main diagonal minus this backwards diagonal. I got a 0. There is no inverse. Can't do this one. That determinant told me that right away. Let's take a look at our last example. 4 times 2, 2 times 3. I can subtract those and get 2, so I know this has an answer. So my inverse for this matrix, I put 1 over my determinant, so 1 over my 2. The 4 and the 2 switch places. The 2 and the 3 stay put, but they are going to change signs. And you're fine to leave the matrix like this. If you want to multiply that 1/2 in, you certainly can. Both answers are acceptable for the inverse of a 2 by 2 matrix.